Hello, and welcome to this lesson on energy profile diagrams. In today's lesson, we will understand the significance of energy profile diagrams in visualizing and interpreting chemical reactions. We will then go on to identify the key features of endothermic and exothermic reaction profiles, including activation energy and enthalpy change. So far, you've learned that exothermic reactions release energy into the surroundings, usually in the form of heat, while endothermic reactions absorb energy from the surroundings. Building on this foundation, today's lesson will enhance our understanding of how energy changes during chemical reactions can be visualized using energy profile diagrams. This deeper insight is crucial for predicting reaction behavior and manipulating conditions to control chemical processes. Energy profile diagrams plot the energy levels of reactants and products over the course of a reaction. These diagrams help us visualize how energy changes during a chemical reaction, from the reactants to the products. The x-axis typically represents the reaction progress, while the y-axis corresponds to the heat energy. Two main features of energy profile diagrams are the activation energy and the overall energy change, also known as enthalpy change. Let's first examine activation energy. This is the minimum amount of energy required for a reaction to occur. It is like the initial push needed to start a task. On an energy profile diagram, the activation energy is represented by the peak that occurs between reactants and products. It indicates the energy barrier that must be overcome for the reactants to transform into products. We will further elaborate on activation energy in the next lesson. Moving on to enthalpy change. This is the overall energy change of the reaction, encompassing both energy absorbed to break bonds in the reactants and energy released when new bonds form in the products. Enthalpy change can be either positive or negative. The shape and position of energy profile diagrams also allow us to determine whether a reaction is endothermic or exothermic. In endothermic reactions, reactants absorb energy from the surroundings, leading to an increase in energy level. Hence, the energy level of products is higher than that of reactants. Accordingly, the overall energy change is positive and represented by an upwards arrow, indicating that the reaction absorbs energy. Let's now examine exothermic reactions. In exothermic reactions, reactants release energy to the surroundings, resulting in a decrease in energy level. Hence, the energy level of products is lower than that of reactants. Accordingly, the overall energy change is negative and represented by a downwards arrow, signifying that the reaction releases energy. By mastering the interpretation of energy profile diagrams, you can effectively understand and predict the energetic dynamics of chemical reactions. Let's now consolidate this knowledge with some practice questions. Given the energy profile diagram provided, identify whether the reaction is endothermic or exothermic and justify your answer. First, let's examine the energy levels of the reactants and products. If the energy level of the products is higher than that of the reactants, the reaction is endothermic. If the energy level of the products is lower, the reaction is exothermic. In the provided diagram, you can see that the products are at a higher energy level compared to the reactants. Therefore, this reaction is endothermic because the products have more energy than the reactants, indicating that energy has been absorbed from the surroundings. Now, let's have a go at calculating activation energy. Using the provided energy profile diagram, calculate the activation energy for the reaction. First, identify the energy level of the reactants and the peak of the energy curve from the diagram. The activation energy is the difference between the peak energy and the energy of the reactants. So we have activation energy equals the energy of the peak minus the energy of the reactants. From the diagram, we see the energy of the reactants is 50 kilojoules and the energy of the peak is 150 kilojoules. So activation energy equals 150 kilojoules minus 50 kilojoules, which equals 100 kilojoules. Thus, the activation energy for this reaction is 100 kilojoules. Next, let's have a go at calculating the enthalpy change. Given an energy profile diagram, determine the enthalpy change of the reaction. First, we identify the energy levels of the reactants and the products from the diagram. The enthalpy change is the difference between the energy of the products and the energy of the reactants. From the diagram, we see the energy of the reactants is 60 kilojoules and the energy of the products is 20 kilojoule. So, enthalpy change equals 20 kilojoules minus 60 kilojoules, which equals negative 40 kilojoules. The enthalpy change is therefore negative 40 kilojoules, indicating that the reaction is exothermic since enthalpy change is negative. By working through these examples, you've seen how to identify reaction types, calculate activation energy, and determine enthalpy change using energy profile diagrams. These skills are crucial for interpreting and predicting the energy changes in chemical reactions. In today's lesson, we delved into the importance of energy profile diagrams for visualizing and interpreting chemical reactions. We explored how these diagrams graph the energy levels of reactants and products throughout a reaction, with the x-axis representing reaction progress and the y-axis indicating energy levels. Key features of these diagrams include activation energy, the minimum energy required to start a reaction, and enthalpy change, the overall energy change of the reaction. By visualizing and interpreting these diagrams, we can better understand the energy dynamics of chemical reactions and predict reaction behaviors. This lesson has enhanced our ability to use energy profile diagrams as a tool for understanding and predicting the energetic changes that occur during chemical reactions.